Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thank you to the organizers, and also thank you to Microsoft. Hello to Kristen, wherever she is out there in video land. And so I'm going to talk about work which is joint work with Joe Silverman, actually when he was at Microsoft Research. He spent a semester at the Cambridge branch, piece, whatever it is, and this was from then. So I'm going to start with a motivation which I'm then going to forget for the rest of the talk, because I think the question that comes out of it sort of takes on its own interest. But let's start with this. So suppose we have an integer sequence. And I want to look at the indices n such that n divides the nth term. Okay? So I'll call it the index divisibility set. And obviously the interest of such a question depends greatly on what sequence you're looking at. So for example, if your sequence is b to the n minus b, these already have a name, pseudoprimes to the base b. And I want to look at the structure of the set by making it a directed graph. So you can take the elements, the indices which divide their terms as the vertices, and then draw an arrow from n to m if n divides m and n is smaller than m, and if it's a direct connection, so there's nothing in between, which is also in the set. So this was actually, Chris Smith took a look at this for Lucas sequences. So these are just linear recurrent sequences, anything that satisfies a linear recurrence like that, where a and b are whatever coefficients you want. If you call delta the discriminant a squared minus 4b, then you can describe this set in terms of all the arrows in the graph. So suppose you have some n in the index divisibility set, and then you can classify all the arrows originating at that vertex. So you have an arrow heading from n to n times p, where p is prime, whenever that prime is a divisor of that particular term, L sub n, or divides the discriminant delta. And then you have a few extra ones in there, which are classified down here. So sometimes you can go from n to 6n or 12n. So we saw this paper, and we thought of asking the same question for elliptic divisibility sequences, which are related to elliptic curves. So suppose we have an elliptic curve and a point on the curve, both defined over the rational numbers. Then the point, the x-coordinate of the nth multiple of the point. So I'm told that not everybody in this room is a number theorist, so I'll sort of toss out the basic facts about elliptic curves. An elliptic curve, well, its points form a group, which I'm sure you've all heard, even if you don't enjoy studying them all the time. So this means the nth multiple of that point, and looking at the x-coordinate. So because of the form of the equation there, the x and y coordinates will have denominators something squared and cubed, and we'll call that something dn, and we'll just extract those numbers, those integers, take the positive integer, and make that a sequence. Okay? And this is called an elliptic divisibility sequence, and I won't talk about them for the rest of the talk, but I'll just mention that they carry a lot of the information about the elliptic curve. So you can see a lot of things going on in the elliptic curve just by looking at these sequences. Okay, so these were the sequences we were interested in looking at. And we got a theorem which is not dissimilar to what Chris Smith got. So you can ignore some of the technical stuff here, but let's suppose we have an elliptic divisibility sequence. Then you do get an arrow from n, so looking at part 1 there, I guess they give me a laser pointer. Part 1 here. You do get an arrow from n to n times a prime when the prime divides the nth term, just like in the other theorem. Yeah?
One slide.
Yep.
One question. So the index n indicates the multiple, and then
Yes.
where's the sequence a? I mean, it's referring also to one fixed.
Yes, exactly. You pick a fixed curve and you pick a fixed point,
Yes.
and then you get a sequence of integers. So for every curve and point, you get such a sequence.
Yes.
Yeah, thanks for clarifying that. Okay. Yeah, so we're picking a particular elliptic curve and a point and looking at the associated sequence. And then if you have some vertex in your graph, then you get an arrow from that from n to n times p if p divides that element of the sequence. And you also get some extra arrows. You get n going to n times d, where d is what I've highlighted in red there, an Aliquot number. And this is not Aliquot in the classical sense. This is our own. We decided to call these Aliquot for elliptic curves. Okay. So I'll explain what that is in a second. But I just wanted to highlight the relationship to the previous theorem here we get when you divide the term, and then some extra special stuff. Okay. And the special stuff for these sequences is Aliquot numbers. And then parts 3 and 4 here are sort of the converse. So if you have an arrow going from n to n times a prime, then it did usually come from either dividing the term or being an Aliquot number, the prime itself. So when I say good reduction here, what I'll talk about in the rest of the talk is I'll be talking about taking an elliptic curve defined over Q and then reducing it modulo P and getting something defined over FP. And then the question is whether you still get an elliptic curve. If you do, then you call it good reduction. You could get something singular, and that's called bad reduction. And the last one here says if you have an arrow with a composite multipole, then in certain cases you can say that that's an Aliquot number. So it's not a full converse to this. So when we were looking at this, we came up with these Aliquot numbers naturally from working on that project. And now I'm going to forget that project completely and define what and move from the definition of an Aliquot number right to something just talking about the elliptic curves that's a question in and of itself. So what do I mean by an Aliquot number? So if you have some primes of good reduction, all distinct primes, and the first index at which pi appears as a divisor is pi plus 1, okay? For each link in the entire loop, so including that the first index at which pl appears as a divisor is p1. So going right around. Then the product of those things is called an Aliquot number. Okay. And the important piece of the elliptic curves that you see in the sequence is that if your prime divides the nth term of the sequence, that means that the nth multiple of the point to which this sequence was associated is 0 mod p on the reduced curve. Okay? So where the primes appear in the sequence is telling you the order of the point. And so in particular, if you just have the order of your curve being prime, then your point has to have, if it has non-trivial order, it has to have that order. So, so you can get Aliquot numbers, you can build such things by finding elliptic curves that when you reduce mod the ith prime have a number of points equal to the I plus first prime. Okay? And the special case of this where there's just one prime and it references itself is where the number of points when you reduce mod p is actually p. And that's already got a name, that's an anomalous prime. So that's in particular an Aliquot number by this definition here. So you can forget all of the stuff about sequences and just ask the question for pairs to start with. So when can you have two primes so that when you reduce modulo one of them, the number of points on the reduced curve is equal to the other? And so this is in vague analogy to the classical number theoretic meaning of amicable numbers, but not in any meaningful analogy. Okay, so here's a couple examples. So these were just searches. We took a couple curves of small conductor and looked for such pairs up to 10 to the 7. And in one example, we found one pair, and in the other example, we found 4. Okay. And so this is a little background slide for those who want a little bit more about elliptic curves. If we have an elliptic curve over a finite field, let's say Fp, then we define the trace of Frobenius to be the difference between the number of points on the reduced curve and p plus 1, because the reduced curve should have about p plus 1 points, but there's some variation. And the variation can be bounded. We call this the Hasse interval, in which that thing called the trace of Frobenius can lie. Okay? And we have a theorem of Düring that says that everything in that Hasse interval can be attained if you pick the right curve for a particular prime. And also we have some conjectures which govern the distribution within that Hasse interval as you vary over different curves. So we can ask about the number of the number of amicable pairs up to a given bound. So this is for a particular curve E. So I'm giving this counting function Q, which is indexed by our particular elliptic curve E. And the first question is just how does this grow with x? So how many amicable pairs do you expect there to be? And the question is sort of a strange one. You don't really expect amicable pairs to occur for any reason other than just kind of randomly when you ask the question, right? So, but it turns out that this actually has kind of an interesting answer. The second question here is maybe we can relate it to a counting function which has already been studied, which is, I'll call n, which is the number of primes so that the reduction is prime. If you're going to have an amicable pair at all, then in particular, when you reduce modulo p, you have to get some other prime q. Okay? So we can count the number of primes for which there's prime reduction up to some bound, and then we could maybe compare the two counting functions. Okay? So here's a sort of I put the counting function up at the top just for reference there. And there's a conjecture due to Koblitz which gives a conjectural growth for this with respect to the bound. So it's x over log x squared. And the constant there, he actually gave some conjectural values for that constant in different cases. And Zuina gave some corrections to that portion of the conjecture, so I stuck his name up there as well. And in particular, the conjecture is that that constant is 0 when there's only finitely many primes, obviously, but that's the only time when it's 0. You could have, for example, you could have over your original curve over the rationals, you could have some torsion, and that torsion is going to survive reduction mod p and divide the order of the reduced curve all the times, in which case this you wouldn't expect to be growing. So here's a sort of vague heuristic for how many amicable pairs you should expect. So we'll do it in terms of probability. So the probability that p is part of an amicable pair. Well, first of all, you have to reduce modulo p and get some prime order. Call that q, and then reduce mod q and see if you get back p. So let's just assume that those two things are sort of independent. And if that's the case, then we can analyze each of those probabilities separately. And turning around the conjecture of Koblitz, we get that the probability that when you reduce mod p, you get something prime should be somewhere around log p. And we also have that the probability when you reduce modulo some particular prime q that you get a particular value you had in mind, which was p, should be about 1 over root q, which is about the size of root p. P and q here, if you're going to be in an amicable pair, they have to be about the same size because they have to be in each other's Hasse intervals. Okay, so that tells you that, yeah.
Estimates are up to like
I'm not, I'd have to look. No, I'd have to go back. I don't remember the.
What's that notation mean?
I think that, yeah, I think that's an unusual notation that we used in that. It means that there's a constant in both directions, I think. Okay. Yeah, I think the referee said that's not a normal notation for this.
I think usually it's like the smile and the frown.
Yeah.
That one.
Yeah, that's a more usual notation for this thing. So putting these two things together, then we should have the probability that p is part of an amicable pair should be around 1 over root p log p. So we turn that back into a growth function, and we get something like that the number of amicable pairs should grow something like root x over log x squared. So if you remember, the conjecture from Koblitz was x over log x squared. So this is smaller, which you would expect, right? So the first conjecture then is, well, let's just put this together. So there's the counting function for amicable pairs. Assume that you actually get infinitely many primes so that you have prime reduction, because otherwise you're not going to be able to count more than finitely many pairs. And then we expect it to grow like that, where these constants should somehow depend on the curve. But who knows how. So I think that if somebody asked you this question about amicable pairs, you might do this heuristic, come up with this growth rate, and then be like, okay, well, probably can't prove this, and probably that's about the story. It kind of happens randomly, the amount of time you'd expect it to happen. I guess we can check against a little bit of data, but we don't have very many pairs to count. So for this particular curve, and thanks to Andrew Sutherland who extended our calculations beyond what we could do, and none of this was done with Sage as far as I know. We can count the number of pairs, and we only get even 117 up to 10 to the 12. So we could compare our counting function to root x over log x squared, and I'm not sure that the data is very convincing. We could compare it to log x there. This should go to like a half or something. Not very convincing. So we just don't have enough data to even know. Okay? But let's look at another example. So these were the two that I had on the first time I put up some examples. So up to about 10 to the 7, we get 1 in one case and 4 in the second case. But for this curve down here, we get 5,578 in the same range, of which I have not listed them all. So that curve, you may, if you're familiar with elliptic curves, you might notice that's a curve with complex multiplication. So something special might be happening in the case of complex multiplication. So I'll just tell you what complex multiplication is. Usually, if you look at the endomorphism ring of your elliptic curve, it's usually isomorphic to z. You have an endomorphism given by multiplication by m for each possible integer m. But sometimes your endomorphism ring is the order of an order of class number 1 in some quadratic imaginary number field. So sometimes you get curves that have more interesting endomorphism ring, and those are called curves with complex multiplication. So we can actually prove something. We can say, suppose we have a curve with complex multiplication, and suppose we have the complex multiplication is given by this field q join root minus d, some order in that field. And let's throw out the j equals 0 case, that particular case. And let's suppose p and q are primes of good reduction, so not too small. And suppose we already know that when we reduce mod p, we get prime order q. And the question is, does q reciprocate? Does it return the love, right? When you reduce mod q, do you still get p? If so, then that would be an amicable pair. And it turns out that, in fact, when you reduce mod q, only two things can happen. Either you do, in fact, get p back and you have a pair. So this is the case where you have a pair. Or you can get this other quantity. And if you're familiar with this sort of thing, you'll probably recognize this formula. What this is saying, actually, is that the non-trivial quadratic twist over the finite field has p points. So you always get e and e tilde, and one of the two has p points. So I'll quickly give you the proof. It's on a slide. First of all, we're interested in, going back to the statement here, we're interested in getting prime reduction, right? We know that when you reduce mod p, you get q. So we're going to throw out curves with 2 torsion, because those will survive the reduction mod p, and we won't get prime order for the curve. So that leaves that d is congruent to 3 mod 4. There's only finitely many different cases, so I forget how many this leaves, but anyway, when we look at p, it has to split. Okay, this is because the inert case corresponds to supersingular reduction, and in supersingular reduction, the number of points would be, in particular, even. So p splits, and if we look at the number of points, so p splits as frac p and its conjugate. So if we look at the number of points over fp, then this is just the usual formula. The number of points in the curve is p plus 1 minus the trace of Frobenius, where this Grossen character gives you the Frobenius as an element of the order in the number field that you're identifying with your endomorphism ring. So this expression up here in number 3 there, that's the norm of 1 minus psi of p. So anyway, in particular, we know that this reduction is q, that this reduction modulo p is q. And so that says q is the norm of something in this order. So that means that q itself splits. And then we can look at the norm of psi of q, which is also q. So that means those are 2 different things which have the same norm. Now, up to picking which of the q or q bar we want here, that means that those two things are the same up to a unit. Okay? And in all the cases that we're in, because we threw out the j equals 0 case, it turns out that the units available to us are just plus or minus 1. So then you can just calculate the trace of Frobenius for Q. And in each of the two cases, you get two different values, and they correspond to these two cases. So it comes from the complex multiplication structure, which is this rich structure that we have in the case of CM curves. So let's look at the data. So these are the different possible orders for the endomorphism ring. Okay, D it was Q adjoined root minus D, and F there is the index of the order. And that's the bound, and those are the number of pairs. So this is just the counting function up here. And then let's actually look at the ratio of the amicable pair counting function over the counting function for prime reduction. So what the theorem said was that if you already have prime reduction, then there's two possible cases, and one of those cases corresponds to you being an amicable pair. So you'd expect this to go to a half, except that the pair counting function has two primes for each pair. So you actually expect it to go to a quarter. Okay? And here it does look, I'd say, at least encouraging. Okay. So that looks good. It looks like basically what this table is saying is that in the statement of the theorem, going back for a second, it looks like these two cases really do sort of happen equally often, which would be your first guess, I suppose. So here's the conjecture then that we get to put together. We have the not complex multiplication case, which is what we had before. And then if it has complex multiplication, then we expect it to go to a quarter of the counting function for prime reduction. Okay. So you could ask about Aliquot cycles. You could ask about more than just pairs. So suppose you have a whole sequence of primes such that when you reduce modulo one of them, you get the next one, all the way around and coming back to the beginning. So here's a couple examples. This one was found just by searching, and this one shows signs of being constructed. Take a bunch of primes that fit inside each other's Hasse intervals so they could at least plausibly be a cycle, and then you can construct such a thing. Actually, it's not too hard to do something like this. First, just make sure they all, satisfy, their sizes are good enough so that the Hasse interval condition is verified. And then for each prime, you can find by jurying some elliptic curve that has the correct reduction over FPI. So you get one curve for each of them, but of course then you can just use Chinese remainder theorem to get some curve that reduces to all of those. And that's why you get these giant coefficients. So that's how we made that example. Now, in the CM case, it's actually interesting that you don't get any. So in the CM case, we had lots of pairs, but you don't get any longer cycles. And that's, again, from that same CM theorem that we had before. So supposing you were trying to make a long cycle, long meaning 3 or more primes. Well, we know from that theorem that there's two choices in the reduction at each stage. So when you put those together, you get a recurrence relation telling you what the next prime could be based on the previous two. So if you put together the recurrence relation, you can get a general term. You can find out, in fact, that each term, that P1 is P2 plus some positive amount. L is the length of the cycle here. So if L is at least 3, this is some positive number. So it means P1 is P2 plus some positive amount. So P1 is bigger than P2. And similarly, P2 is bigger than P3. P3 is bigger than P4. And you can see where I'm going. It's like the Escher staircase, right? You can't come around and be bigger all the way around your cycle. Coming back to where you started. So you can't make bigger cycles in the CM case. All right, so the last, the case that I left out of the CM theorem was the case of the j equals 0 curve. So this curve has a little more interesting number theory. And so I'm going to look a little more closely at what happens. And in fact, it turns out that there's a really interesting, purely elementary number theory question that comes out of this, which I'm still looking for an answer to. So here we're working with q adjoins square root of minus 3, which has a sixth root of unity. Okay, that's why the previous proof there required that the units were just plus or minus 1. So here we have more units. The unit group has 6. And in fact, the ring of integers can be made just by adjoining that omega there. And this has a nice property that the unit group with 6 elements, if you reduce modulo 3, those 6 elements go 1 each into each of the invertible classes. So that's an isomorphism. And we can also talk about the sextic residue symbol when we're working here, which is defined down here. It's just like quadratic residuosity or a cubic residue symbol. Okay. So in particular, for any element, you're getting some sixth root of unity as your sextic residue symbol. So this is the number field that we're working with for the j equals 0 case for the endomorphism ring. And so we get a similar theorem to the CM theorem that we had for the other CM curves. Now I've stuck some of the proof into the statement here because we can give explicitly what the unit is. So in the CM proof I just said there's some unit, it's either plus or minus 1 in the middle of that proof. And here we can actually describe what that unit is. So just going back over the setup here, we have some elliptic curve. For j equals 0, we can write y squared equals x cubed plus k. And suppose that p and q are primes of good reduction. P is not too small, and that when you reduce modulo p, you get q points. Then, as in the proof before, p has to split, and you can take q to be the ideal generated by 1 minus the Frobenius. So then q also splits. And then we have these frac p and frac q to talk about, and they're related by a unit. So just as in the previous proof. But now that unit is actually given in terms of these sextic residue symbols of k, just from the k as in the equation for the curve. So if this unit comes out to be 1, that's the case where we get an amicable pair. So if we already had that when you reduce mod p you get q, we also get when you reduce q you get p when this thing comes out to 1. Okay? So there's 6. So the moral of the story is there's 6 possible options for this unit, and one of them is the case of an amicable pair. So you would expect that a good first guess, just like in the other CM case, is that these 6 units occur evenly often. And so you would get the relationship between the pair counting function and the prime reduction counting function would be 1/12, accounting for the fact that there's 2 primes in a pair instead of 1/6, right? So, okay. So just a couple extra remarks about this. Just as in the original CM case, those 6 different units correspond to twists. So that's 6 different possible values also, just like in the statement of the other CM theorem that you could get for reduction mod q. So you can state it that way if you like. And the reason that we actually can give this explicitly is from the theory of CM, we know the Frobenius as a sextic residue. So here's the data. Okay, we've got different values of k across the top. We expect the ratio of q over n to be going to about 1/12. And it looks suspicious. For k equals 2, we seem to be getting a quarter again, like before. For k equals 5, it looks reasonable. And the other ones, it's not clear what they're doing. So something more interesting is happening with this unit in this case. So then the question is just to take a look at this unit and see if we can analyze what we would expect it to be doing. If it's not going to be distributed evenly as k, distributed evenly for different p, then for a fixed k, then what do you expect it to be doing? So let's look a little more closely. These are the 6 possible values. Here's a giant amount of data. So this corresponds to the unit being 1, and this corresponds to the unit being -1. And then these are the other 4 possibilities for that unit. And down here we have the different values of k, and then these are just the frequencies of falling into those 6 different possible cases. So I think looking at the data here, well, what I noticed, and then Joe wasn't so convinced, was that it seemed to me that 1 and 2 were always a little bit more than the other cases in each of them. But it certainly seems as if these two columns are about the same as each other, but then they differ somehow from the other 4 cases. Look at the data. Some of them it's really clear. For example, for k equals 2, we don't even get those other cases. And those 2 cases seem to divide about evenly. And for this one, for k equals 3, for example, it's also looks fairly clear. Some of the other ones, not so sure. It certainly seems to depend on k a lot. So. OK. All right. I don't know how I'm doing for time. Oh, there's a clock at the back. OK, so let's. There's just the pieces of the info for our number field up at the top there. And we have cubic reciprocity, which I'm going to use in a moment. So I thought I'd state it nicely. This is my favorite way of stating quadratic reciprocity, which is to think of the primes instead of being just the positive primes. Think of the primes as -3, 5, -7, -11, and so on. If you put those signs on the primes so that they end up being 1 mod 4, then you can state quadratic reciprocity particularly nicely. So this is the way that I've stated cubic reciprocity. I've chosen the representative for a prime ideal to be so that it's 1 or 2 mod 3. Yeah, okay. So we have this unit that we'd like to analyze. Okay, so this is what it looked like from the statement of the theorem. So from cubic reciprocity, we can flip numerator and denominator, of course, to check all the details and whatnot. So there's a little bit missing, but we can turn it into this. Okay, and so here I've got sextic residue, but I'm just going to ignore the quadratic part. And just put a plus or minus in front. I'm really interested in the cubic part. And the reason for that is that when we looked at that table of data, it looked like plus or minus 1 were behaving pretty evenly. So it's really the cubic part which is the mystery. Okay? So changing this around, we get this symbol here. Okay? So we're interested in this symbol where m is our Frobenius for different primes p. So a first guess might be that the Frobenius ranges evenly through whatever elements it would be allowed to be as p varies. So you could take all of the m for which m times 1 minus m is invertible, and then you could look at how many of those actually give this cubic residue coming out to 1, and you could ask whether that's actually a third or that's some other ratio. Okay? And when this comes out to 1, that corresponds to the case where this thing becomes plus or minus 1, and we're in those first 2 columns. And we're seeing that we seem to be in the first 2 columns more often. So is that simply because there are more elements, m in the residue here, in the residue ring, that m times 1 minus m is actually has cubic residue 1. Okay? So then the conjecture would be that we expect this counting function ratio to go to that ratio, where we have a 4 accounting for the fact that now we're allowing plus or minus 1, and we're still counting 2 primes in a pair. Okay? So don't worry about the 4. Really, we're interested in this ratio of mk star over mk, okay? Where mk star is the one where this is cubic residue 1, and mk is just all the things where that numerator is invertible. So this becomes a purely number theory question. Now we've sort of forgotten about the elliptic curve completely, and we're just asking for different k's. How can you count this? Okay. So here's an example of how we can count it when k is congruent to 2 mod 3. All right. So if we want to look at when m times 1 minus m is a cube, has cubic residue 1, then we have to look at the associated, well, one way to do it might be to look at the associated curve, y times 1 minus y is x cubed, right? How many points are there on that? And that just happens to be a j equals 0 elliptic curve. I don't think this is for a reason, but it just happens to be. So we have then that this curve E, related to our problem, is for k, when k is a prime congruent to 2 mod 3, this is actually super singular, and counting the points is really easy. Okay, so if we want to count the points over k, that's actually fk squared is the residue we're interested in. So it has k plus 1 squared points, okay, for It's really easy to count the points over a supersingular curve. If this wasn't supersingular, if we had 1 mod 3, then we would have some trace of Frobenius in here instead of a fixed number in terms of k. Okay, so then we just want to count the points on that that correspond to solutions. So we have to throw away the points infinity, 0, 0, and 0, 1, because they don't really correspond to solutions for what we're looking for. We want this numerator to be invertible, so we have to throw away y as 0 or 1. Okay, so take away those 3 points. So now we have k squared, k plus 1 all squared minus 3. And then, of course, we're triple counting because x can be 3 different cube roots for each y. And we just want to count the y's. So we divide by 3. So that's the number of solutions to the problem then. Okay, so number of residues not equal to 0 or 1, having that being a cube. And so that lets us count those things. Okay. So the question, so this particular case fits on a slide, but all the other cases, as we went, just got worse and worse and worse and horribler and horribler and horribler. Okay. So of course, if, like as I said, you can get traces of Frobenius in there that you have to be counting somehow. You have this strange thing that happens, which is sometimes your Frobenius doesn't want itself to be a quadratic or cubic residue. So sometimes you actually want to count a slightly different thing than what we were just counting. And when you do the point counting, when it's avoiding a quadratic or cubic residue, then you end up having to go to some other curves, not necessarily just that elliptic curve we were looking at. And so it ends up you can break up k for k prime up into different cases mod 36. And you can actually work it out, but the calculations were so messy that we actually had the computer do the computations in the end, all the simplifying and stuff. And if k splits, of course you have to do the 2 cases separately and combine. If it isn't prime, you have even more complicated stuff to look at. So I won't.
What's the relationship between these curves and the started with?
So there isn't really. The only reason I'm bringing this curve into it is because this is the numerator of a cubic residue, and I want it to be a cube. Right? So when you want it to be a cube, but you also don't want this to be a quadratic residue or a cubic residue, then you can count the number of points on that other curve and then take away the ones that would fit on this with n equals 2. And so, okay. But basically, we turn it into a number theory problem and then ask that problem naively and forget the original curves to do with the pairs. Okay. So those computations are a challenge. And now I'm putting up the guts of the actual answer in case anybody wants to actually see it written down. So basically, instead of the MK, which was just, here, there's 4 cases. Here's the second slide. The last case here, where k is congruent to 3 mod 4, or k, the prime factors of k, are not congruent to plus or minus 1 mod 9. So this means each prime factor. Then the MK you want is the original one. So just the fact where those are invertible in the residue. And then for these other ones, you have cases where it might not be a cubic residue, might not be allowed to be a cubic residue, or allowed to be a quadratic residue. And it just depends on the behavior of k mod 4 and mod 9. Okay, and then again, MK star is just all the things in MK, but where that's a cube. So that's the technical details to writing this out. And then once you have those definitions, we expect the limit, going back to the amicable pairs question, we expect this limit to be a quarter of the limit of those counting functions. Okay. And that doesn't even deal with the case when k is not coprime to 6. So here's what it comes out to when you actually count all these things. Okay, it took pages and pages in the paper, and then it simplifies to these simple polynomials in k. So when you do the computations, you're counting points on all of these curves and these Jacobians, these crazy curves and stuff, and you do all this stuff. These traces of Frobenius are showing up. All of these residues are showing up in the calculations. Somehow they all cancel, and you get something that's just polynomial in k in the end. So when we count these things, we get 1/6 plus a half of whatever polynomials in the different cases. And so in the one case that I showed that worked out when k was 2 mod 3 and prime, it wasn't maybe surprising it came out to a polynomial in k, but for these ones it really is, because the computation is, there's no reason to expect all that stuff to simplify. And I feel like there should be some real good reason for this that I'm just not, I don't know what it is. And it's a purely, you can state this problem purely in the case of, as a number theory problem. And if the answers are so simple, I feel like there should be a good reason. And our reason is not a good reason. So finally, here's some data for this conjecture. So we went and computed these, what we expect the conjectural limit to be. And for each k, it's just some rational number. So here are those rational numbers for each k. And these two columns compare conjecture and experiment. And I think it's pretty convincing that we seem to have discovered that the Frobenius is ranging through at least those allowable classes according to the, according to the way described. So it seems plausible, and fortunately with these curves we can get lots of pairs. This is the number of pairs, so that gives you an idea how robust the data is. So that's up to 10 to the 8. So seems reasonable. So these are the final suggestions, ideas, questions, I don't know, that might come out of this project. So first of all, this first remark is just what I was saying a second ago. These things I'm computing, the number of classes where this thing is a cube, are coming out to these very simple answers, and I don't know why. So one could ask that question more generally. So we had m times 1 minus m, but what happens if you have some polynomial in terms of m up here? I don't know what's known about that question in general. And so, I mean, I'm new to SAGE, but it seems like we could ask about what SAGE can already do with respect to these computations. We didn't do them in SAGE, but we did use the computer. We used Paris to do the computations because they were so messy. And could doing these sorts of computations provide any insight and give some nicer answer to why these things come out nicely? Or is it a special case for m times 1 minus m somehow? Another question that comes out of this is to think about this as a dynamical system. So going back to the pairs, it's sort of like taking reduction modulo p is something you could iterate. So you take reduction mod p, you get q, you take it with q, you get back to p, and you have a 2-cycle. So, but of course this isn't, we'd have to define this more generally, because what if you reduce mod p and you get some composite number? What's the next step? What's the function you want to iterate? That's reduction mod p for primes. So one idea is to define for, instead of your trace of Frobenius only for p, define it for composite numbers in terms of the L series. And a student of Joe Silverman, Hatice Sahinoglu, is working on this. So we shouldn't steal her problem. But there might be other ideas for how to think about this as a dynamical system. This might not be the right dynamical system. Yeah?
I think it's weird. I mean, n plus 1 minus an seems a little suspicious. I mean, shouldn't it be more like, if n is p times q, you think it would be p plus 1 minus ap times q plus 1 minus aq. So that would be the cardinality of e of f.
Yeah, I have
e
this.
of z mod nc.
Yeah, I have the same thought that this is suspicious. Yeah, it's fishy. So there are certainly other alternatives. And yeah, that seems a little more natural to me. I also thought of somehow, well, anyway, there's other.
Like the cardinality of e of f. The cardinality of e of z mod nc.
Yeah, exactly. Yeah.
We're not sure.
Yeah, but then what do you do? Well, yeah, okay. So, so that's definitely something to ponder. Also, one reason that we found this interesting was because if a prime is anomalous, it's actually a very special case. So if you have an elliptic curve over fp where p is anomalous, it's susceptible to an attack for the elliptic curve discrete log problem. And so if you have an amicable pair on your elliptic curve, is there anything you get from that? We couldn't get anything, but it's an interesting question. And of course, I don't know, we could figure out other ways to construct pairs, cycles, or better ways to search for them. We just really did exhaustive searching just by reducing and checking what the order was. So, yeah. So, thank you.
Yep. Does anybody have any questions? So, question?
Sometimes when you look at these distributions and compare them with the certain matrix groups and counting how often those matrices have certain eigenvalues, probabilities end up matching up really nicely.
You're talking about this question here?
You were saying about, your probabilities that you got where you had 1/6 plus, something in K. You're saying, is there any explanation for that? And I was wondering, one place to look for that might be to look in, to see whether there are any matrix groups associated with your problem, and then trying to analyze the probability that those matrices have a certain value as an eigenvalue. And so you'd think that the eigenvalue 1, for example, should occur about 1/p of the time, but it's actually a little bit off from that. And so sometimes that can give an explanation for something that...
Oh, that's fascinating. Yeah, I'd like to find out more about that. I haven't thought about that.
So one thing I noticed was the Chebbit-Herault density theorem didn't pop up anywhere in your talk, but somehow feels like it should if you're trying to prove one of these cases, but it kind of doesn't matter if you're just trying to find a conjecture. But why is that?
Well, I think we did think about it a little bit, but I'm not sure if I have anything coherent to say about it.
And so in every possible case you have a kind of a conjecture now, but you don't have a proof of any cases at all.
Right. All we've got is the proof that that it's sort of restricted in the CM case.
Yeah, but you've given a conjecture in every case now, which is really nice.
I think maybe except for like K not coprime with 6.
Right. A few cases with J0 and Ks.
Yeah.
Are you going to look at all? You can ask the same questions over numbered fields as well, like take class number not equal to 1 CM curves, for example, or
yeah. So we did sort of note that the similar proof will work for CM over, but of course there could be way more complications of this type that you get for the J equals 0 case. So saying something similar works just means the same sort of proof works, but then the actual working it out, what the many cases are depending on the units and stuff, is it.
What about the non-CM case over numbered fields?
Well, there we only have a conjecture, right? Mm-hmm. We don't really have anything.
You can make a conjecture there.
Yeah, we should be able to make...
Because it was easier to make the conjecture in the non-CM case.
Yeah. Yeah, so I guess we should. I don't think...
Might be easy.
Yeah, I haven't tried to write it down. The paper was already like, with all this computing for the J equals 0 case, it was like 50-page paper, and we were like, who's going to want this? Because the first referee came back and said, well, it's interesting, but they don't prove anything. It's 50 pages long. So, which was slightly unfair, but but yeah, it's a lot of just figuring out how to write down the right conjectures.
Also regarding small jack, so I've been talking some with Drew about getting that into Sage, so
cool.
That could be one of the projects. I don't think it would be too difficult to include in Sage, and then at least you might be able to replicate the tables that he made using small jack. So, yeah, some of these.
Yeah, he sent us more data than I have that's up here, but he was just using it. He thought it was good for testing.
Yeah, it's really fast.
To see how fast it was. Yeah, he got a lot farther than we managed to do. We only got to like here or something.
Very basically will go up to 10 to the 8th or 10 to the 9th, and small jack will go farther, and it works in parallel, so it's really nice.
Yeah, so it's pretty nice.
Any other questions? Okay. Thank you.